Great morning, everyone, and welcome to Power Series Part 2, Further Examples. Let's find the radius and interval of convergence of this series, n factorial times 2x minus 1 to the n. So, knowing that this has a factorial and a power in it, that's going to signal to me that it's probably going to be a good idea to try and use the ratio test, which means the very first thing I'm going to do is look at this limit of absolute ratios here and see what happens. Because really, at the end of the day, we want to know for what values of x does this series converge. So we're just going to apply a convergence test to it and then see what the value of x has to be for the conclusion of that test to imply convergence. All right, so an plus 1 is n plus 1 factorial times 2x minus 1 to the power of n plus 1 divided by n factorial times 2x minus 1 to the n. So there's our absolute ratio there. Let's simplify it a bit. I notice immediately that this 2x minus 1 to the n cancels with that one. And I'm also going to rewrite the n plus 1 factorial as n plus 1 times n factorial so that that cancels out. And I have a 2x minus 1 left over. Beautiful. Now I'm going to cancel those n factorials. And I get n plus 1 times 2x minus 1. Use the rules for absolute values. Wonderful. So this is what the limit of absolute ratio simplifies to, the limit of n plus 1 times 2x minus 1. Notice that the limit is only going to apply to the part with the n, and the x is in some sense fixed for whatever value of x I want this to be. And evaluating this limit, I want you to notice that if 2x minus 1 is 0, then this is going to be 0. If 2x minus 1 is 0, then that limit is going to be 0 times whatever value of n I plug in. But if x is not 0 and it's some fixed number, then this limit is going to go to infinity. So this limit is equal to 0 if x is equal to 1/2, and it will be equal to infinity if x is not equal to 1/2. So this limit of absolute ratios is going to be 0 if you plug x equals 1/2 into the power series. And the limit of absolute ratios is going to be infinity if you plug anything else into the power series. So using the ratio test, we have two situations. First, if x is equal to 1/2, then the limit of absolute terms, limit of absolute ratios is 0, which is less than 1, so the series converges. So the ratio test says that if x is equal to 1/2, this limit of absolute ratios is 0, which is less than 1. The ratio test says that means that the series is convergent. However, if x is not equal to 1/2, the limit of absolute ratios is infinity. And the ratio test tells us that the series diverges. So the ratio test has determined for which values of x does this series guarantee diverge and guarantee diverge, converge and diverge. So the interval of convergence is 1/2. And the radius of convergence is 0. This is a situation where the series converges only for one value of x. In this case, x equals 1/2. If x is not equal to 1/2, the series diverges. Let's find the radius and interval of convergence for this series, x to the 2n over n factorial. Again, factorials, exponents, perfect opportunity to use the ratio test, because we really want to know for which values of x does this series converge. So let's evaluate the limit of absolute ratios. Okay. an plus 1 is x to the 2 times n plus 1. Again, be very careful with your exponents here, with your parentheses in the exponent. And I'll divide that by an, aka multiply by its reciprocal. And now let's simplify this expression. This becomes x to the 2n plus 2 over, I'll change n plus 1 factorial to n plus 1 times n factorial. The n factorial and the x to the 2n are there. And now we notice that the n factorials cancel and x to the 2n cancels. And we simplify this to x squared over n plus 1. Which is equal to the limit as n goes to infinity of x squared over n plus 1. Since x squared will always be non-negative, and n plus 1 will also always be positive, because n is a positive number. Well, since x squared is being held constant and the denominator is getting infinitely large, this limit is 0, which is less than 1. So by the ratio test, doesn't matter what value of x you plug in to this power series, the limit of absolute ratios is 0. It's always going to be less than 1. It's always going to be convergent. By the ratio test, this series converges for all x. No matter what I plug in, the limit of x squared over n plus 1 as n goes to infinity is 0. So the interval of convergence, the values for which this series converges, is all of the real numbers. And the radius of convergence is infinity. So it doesn't matter what value of x you plug in, you get a convergence series at the end. Let's find the radius and interval of convergence of this series, 2 to the n times n squared times x to the n. Same old story, we've got some exponent in there, so we're going to use the ratio test. So let's evaluate the limit of absolute ratios. This is nice because it doesn't involve a fraction. Got 2 to the n plus 1. N plus 1 squared, notice that the 1 is inside the parenthesis here. X to the n plus 1 over 2 to the n squared x to the n. Beautiful. Let's simplify this a bit. The 2 to the n's cancel. The x to the n's cancel. And I'm left with the limit as n goes to infinity of 2 times, I'm going to expand this to n squared plus 2n plus 1 over n squared times x. Very nice. I'm going to break this up now. Absolute value of 2 times the absolute value of the limit as n goes to infinity of this fraction times x. Notice that the limit only went into the part with the n's in it. because the limit is involving n's, so everything else stays the same. And this is equal to 2 times, the limit of this is 1 over 1, because there's 1n squared on the top and 1n squared on the bottom, times the absolute value of x, which is 2x. 2 times the absolute value of x. So this is a little unlike the first two examples where we actually got a number when we evaluated the limit of absolute ratios. Now the limit of absolute ratios is an expression involving x. So now we need to use the ratio test to say, well, what values of x will make the limit of absolute ratios, 2x, less than 1 or more than 1? So we know that by the ratio test, this series converges if 2x, which is the limit of absolute ratios, is less than 1. So the ratio test tells me that whenever this limit, which is equal to 2 times the absolute value of x, is less than 1, the series converges. So x less than 1/2. And that means that the radius of convergence here is 1/2. Now let's find the interval of convergence. We do know that this series converges on the interval -1/2, 1/2. Because those are the values of x whose absolute value is less than 1/2. If you have the number 2, which is not in this interval, the absolute value is 2. It's bigger than 1/2. So these are all the values of x whose absolute value is less than 1/2. The question now you have to do is you have to check the endpoints. So the ratio test guarantees that this series converges on this interval, this open interval, -1/2 to 1/2, but the ratio test does not tell us what happens when x is equal to 1/2 or x is equal to -1/2, because the ratio test is inconclusive when the limit of absolute ratios is equal to 1. So we need to afterwards explicitly check what's happening on the endpoints to get the interval of convergence, the full interval of convergence. So let's check the endpoints now. At x equals -1/2, all we have to do is plug x equals -1/2 into the expression and see if the resulting expression is a convergent or a divergent series. So the series becomes 2 to the n, n squared, -1/2 to the n. All I'm doing is plugging x equals -1/2 in and seeing if the resulting series is a convergent one or not. I can bring the two numbers with exponent n together. This becomes 2 times -1/2 to the n times n squared, which is -1 to the n times n squared, which does not exist because this is just going to be a divergent limit. It's going to alternate, but the terms are getting bigger and bigger and bigger. You can imagine it as kind of a alternating funnel. This limit doesn't exist, so it diverges. It does not converge to a value. At x equals 1/2, the series also simplifies to a divergent series, we'll see, because we plug in 1/2, and this simplifies to n squared. 2 times 1/2 is 1 this time instead of -1. And this is also divergent. So yes, the series converges on the open interval, -1/2 to 1/2. But we had to show, and we did show explicitly, that it diverges at x equals -1/2, and it also diverges at x equals 1/2. So the interval of convergence is equal to -1/2 to 1/2. It does not include any of the endpoints. It's just this open interval. This series converges only for values of x in this interval, the interval of convergence. Let's find the radius and interval of convergence for this alternating series x to the n over n squared. Again, no surprise, since we have some exponents in there, we're going to find the absolute ratio and take its limit. And this limit is nice because it's going to get rid of all the negative numbers eventually. Let's see. Negative 1 to the n plus 1, x to the n plus 1, over n plus 1 squared, times n squared over negative 1 to the n x to the n. Good. Let's simplify this a bit. The x to the n's cancel. The negative 1 to the n's cancel. And I'm going to also, in this next step, expand that denominator to n squared plus 2n plus 1. Then I'll have a negative 1 to the 1 times n squared. This is equal to, oh, forgot the x, of course, which is equal to the limit of negative 1 times x times n squared over n squared plus 2n plus 1, which is equal to 1 times x times, there's 1n squared and there's 1n squared on the bottom. So this is equal to x. So the limit of absolute ratios in this example is the absolute value of x. So by the ratio test, this series converges if the absolute value of x is less than 1. Because if the limit of absolute ratios is less than 1, you have a convergence series by the ratio test. All right, so the radius of convergence is equal to 1, and the series converges on the open interval negative 1 to 1. Guaranteed, this series converges for every value of x between negative 1 and 1 non-inclusive. Now we need to check the endpoints to see if it converges or diverges on the endpoints. So we'll check the endpoints. First endpoint, x equals 1. The series becomes negative 1 to the n, x to the n, which is 1 to the n, over n squared, which is equal to negative 1 to the n over n squared. And this is an alternating series. 1 over n squared is decreasing and goes to 0. So this converges by the alternating series test. So at x equals 1, if I plug x equals 1 into this power series, I get an alternating series which converges. At x equals negative 1, I get negative 1 to the n. Now x is equal to negative 1, so I plug negative 1 in instead of x. The negative 1 to the n times negative 1 to the n is 1, and I get 1 over n squared. This is also converges because it's a p series with p equals 2 greater than 1. So at both endpoints, I get a convergent series. This is the complete opposite of the previous example where it was divergent at both endpoints. It's also possible for it to converge at both endpoints. So the interval of convergence, the interval of all x values that make this into a convergent series, is the closed interval negative 1 to 1. Every x value between negative 1 and 1, inclusive, makes this series converge. Let's find the radius and interval of convergence of this alternating series x to the n over the cubed root of n. It's no surprise, given the power that you see there, that we're going to evaluate this limit of absolute ratios. And this is going to let the ratio test tell us what values of x make this series converge. So the n plus first term, negative 1 to the n plus 1 over x to the n plus 1 over the cubed root of n plus 1 times the reciprocal, 1 to the n, x to the n. Beautiful. Let's simplify this a bit. We're going to be able to cancel this x to the n. We're going to be also able to cancel this negative 1 to the n. And now let's rewrite this. We have the negative 1 here. We have the x here. And we also have the cubed root of n divided by the cubed root of n plus 1. Now I'm going to use the limit rules to pull that limit into this expression. So this is the absolute value of negative 1 times the absolute value of x times the absolute value of the cubed root of the limit as n goes to infinity of n over n plus 1. So I combined the cubed roots and then I pulled the limit inside. This is equal to 1 times the absolute value of x times the absolute value of the cubed root of 1. There's one n on the top and one n on the bottom, which is equal to the absolute value of x. So once again, the limit of absolute ratios is equal to the absolute value of x. So by the ratio test, this series is convergent when that absolute ratio's limit is less than 1, or when the absolute value of x is less than 1. So by the ratio test, this series converges if the absolute value of x is less than 1. So the radius of convergence is equal to 1. Let's find the interval of convergence. We know that the series converges on the open interval negative 1 to 1. That's what the radius of convergence tells us. Absolute value of x less than 1 means that it converges for every x between negative 1 and 1, not including the endpoints. It might converge on the endpoints. We have to check that explicitly. So let's check the endpoints. First endpoint, x equals negative 1. What we get is we get the series negative 1 to the n. The x to the n is replaced with a negative 1 to the n. So negative 1 to the n over the cubed root of n. Those negative 1's become positive. Negative 1 times negative 1 is positive 1. So this series becomes 1 over the cubed root of n, which is equal to the series 1 over n to the 1/3. This is a divergent series because it is a p-series with p equals 1/3 less than or equal to 1. So when I plug x equals negative 1 into this power series, the resulting series is a divergent series, a p-series with p equals 1/3. What happens when we plug x equals 1 in? So negative 1 to the n. Now the x is replaced with 1. So it's not x to the n, it's 1 to the n over cubed root of n, which is equal to 1 times negative 1 is still negative 1. And now we get an alternating series, 1 over the cubed root of n. 1 over cubed root of n goes to 0 as n goes to infinity because the denominator gets infinitely large. And it's also a decreasing function. So this converges by the alternating series test. So when I plugged x equals negative 1 in, I got a divergent series. When I plug x equals 1 in, I got a convergent series. So the interval of convergence, the set of all possible x values that make this into a convergent series, it's not going to include x equals negative 1, but it will include x equals 1. So it is possible that one of the endpoints results in a convergent series and the other endpoint results in a divergent series. So it's very important to check the endpoints. Let's find the radius and interval of convergence of this series nx to the n over 2 to the n times n squared plus 1. Lots of powers in here, so let us again evaluate the limit of absolute ratios and see what the ratio test has to tell us. All right, so the n plus first term, n plus 1, times x to the n plus 1 over 2 to the n plus 1 times, be careful with your parentheses here, n plus 1 squared plus 1. Multiply this by the reciprocal, 2 to the n, n squared plus 1 over n x to the n. All right, let's simplify this a little bit by canceling some terms out. The x to the n here cancels, and the 2 to the n here cancels. The rest we're going to have to deal with separately. So what we've got is we've got an x left over, we've got a 2 left over, and then we have an n plus 1, an n squared plus 1. You see, I'm just grouping all the n's together. And on this side, we have 2n squared, or n squared plus 2n plus 2 times n. So you expand that out, you'll get n squared plus 2n plus 2. All right, let's continue simplifying this. X over 2 times n cubed plus n squared plus 1 over n cubed plus 2n squared plus 2n. Okay, we're going to have x over 2 times the absolute value of 1 over 1, because the highest power on the numerator is n cubed, the highest power on the denominator is also n cubed, so that limit is 1 over 1, and the absolute value of 2 is 2. So this is the absolute value of x over 2. So the limit of absolute ratios is x over 2. So by the ratio test, this series converges for the absolute value of x over 2 less than 1, or the absolute value of x less than 2. So this series converges by the ratio test whenever the absolute value of x is less than 2. So this series converges on -2, 2. The radius of convergence is 2. It's centered at 0 because it's absolute value of x minus 0, and any absolute value of x less than 2, it converges. So the radius of convergence is 2, and this is a interval on which the series is guaranteed to converge. In order to see the complete interval of convergence, we need to check the endpoints. So let's check the endpoints. Our first endpoint, x equals -2. All right, so the series becomes n times -2 to the n over 2 to the n over n squared plus 1. I'm going to pull out a -1 to the n there. So -1 to the n, which means what's going to be left is 2 to the n. Let's see. n 2 to the n over 2 to the n squared plus 1. So I've replaced the x with -2, and then I've pulled out the negative part of -2 to the n, and it becomes an alternating series. But we notice that those 2 to the n's cancel, and it becomes an alternating series, n over n squared plus 1. N over n squared plus 1 is a decreasing function that goes to 0. You can check that. So this converges by the alternating series theorem, or test, sorry. At x equals 2, so it converges at x equals -2. At x equals 2, the series becomes n times 2 to the n over 2 to the n times n squared plus 1. The 2 to the n's cancel, and the series is n over n squared plus 1. Now, n over n squared is a lot like 1 over n. And indeed, if you use the limit comparison test with 1 over n, this diverges. And I'll just write that here, and you can check that yourself. Diverges by the limit comparison test compared to 1 over n. You'll find that the limit of n over n squared plus 1 divided by 1 over n is equal to 1. So they diverge together. And since 1 over n diverges, this series diverges too. So it converges at -2 and diverges at x equals 2. So the interval of convergence includes -2 and excludes +2. Finally, as a recap, I just want to make a note that each of the 6 examples we've done demonstrates one of the 6 possibilities for the radius of convergence and interval convergence of a series. It's possible for the radius of convergence to be 0 and for the interval of convergence to include just one element, one value of x that makes the interval convergent. It's also possible that a series converges no matter what value of x you put in, and the interval of convergence is the real numbers, the radius is infinity. It's also possible that the interval of convergence can be some interval, and the interval can be open, so it excludes both endpoints. It can be closed, so it excludes both, or it can include the left or include the right. There are 6 possible types of intervals of convergence for power series.